Good evening. We are slowly coming to the end of the program, but the next talk is the most interesting talk. It not only talks about AI, it talks about quantum computing too. So the title of the session is, What Does Quantum Mean for Research in AI, Longevity, and the Future of Healthcare? All interesting thoughts. So we have Matthew Versaggi to give a talk, and so this session is going to be a little different from the ones we have seen before. There's just one speaker because the topic is profound, and we have an outstanding speaker. So Matthew Versaggi is an AI subject matter expert and senior leader in AI at the Fortune 5 healthcare level, who has seen hundreds of use cases and has been in the AI space since the mid-'80s. He has decades of experience as an entrepreneur, graduate-level university professor, but you have to teach undergraduates to be really a professor, though, yeah. And public speaker, he holds patents in quantum computing, machine learning, and cognitive technology, and has chaired patent review boards that awarded hundreds of AI, healthcare, and technology patents. While serving as a senior director at Optum Technology, Versaggi led the organization's AI Center of Excellence and founded the College of Artificial Intelligence, which has trained hundreds of technologists. Versaggi is classically trained in AI at the graduate computer science level, holds 4 university degrees, including an MBA, and has earned dozens of professional certificates in AI technology and AI business strategy. So I was here all of yesterday, and today morning I had to go to home board to take care of some things, but I noticed that most of the talk was done by people on the stage, the moderators, the panelists, etc., etc. So Matthew and I decided after his talk is over, we're first going to give you the opportunity to grill him about quantum computing and AI and so on. And if you kind of get a little tired, then I have a bunch of questions to ask. So we're going to have you all play the role of moderators, so entire group. So stay awake, and we can have some fun. Matthew.
Well, that certainly seems like an invitation to play Stump the Presenter. Let me just move this. So keep in mind, you guys are going to be participating in this. So grab your questions, sit back, and enjoy the show. We're going to talk about quantum computing. I've got all this AI background, and I'm going to talk about any of that today. We're going to talk about something completely different. I've got 5 years into quantum computing as well. We're going to bring this kind of down to the layman's level is really kind of the idea. If you're a senior leader in that space, we want to kind of make this available to you. We're going to talk about things like the VUCAD world. Don't worry about that acronym. I'll explain it to you. What some of the key technologies are. Walk through Quantum 101, key definitions, terms, things like that. We're going to do a lot of comparisons to classical computing and quantum computing. That's how you can begin to appreciate these kinds of things. We will give you a frame of reference to drop all the noise that you hear out there. We've got one frame of reference that really does a job on that. Give you state of the art, like where is it really at? We'll do some live demos, qubits, quantum circuits, speed and search, those kinds of things, and a few others to kind of round out the day, and then we'll move right into kind of Q&A. So let's get into this. Context building. VUCAD world, virtual, uncertain, chaotic, ambiguous, and digital. It's a nice little acronym. We love our acronyms here in DC as well as in the private industry. It talks about a very harsh political, economic environment the world's rushing into very quickly, whether you like it or not. I'm not going to go through the whole thing. The top of that, though, is a global technology arms race. You're going to see this everywhere. And it's not just digital tech. It's biotech, it's nanotech, and quantum tech is kind of rounding that out. But that global technology arms race is embracing the whole world. You need this as context to understand what we're going to, or to better frame the kinds of things we're going to bring back to you. All the rest of this is details at the footnote of that. But we're going to look at a basket of technologies to frame this. You've been talking about AI quite a bit all day. Biotech and nanotech are key aspects too. Those 3 things are general purpose technologies. They have changed the world, power, wealth, and societal structures every time they've appeared excuse me, on the landscape. Imagine what the world was like before electricity, before rubber, before the steam engine, before domesticated animals, things like that. That's what a GPT does. Quantum, on the other hand, is not one of those, but it affects this. So we're going to look at this basket of capabilities as we begin to kind of look at this space. But I want you to have that as context. We're going to reference this as time goes on. So what's quantum computing? At the end of the day, we're looking to rip out the binary architecture, the hardware that you've all grown up with for your entire lives, from putting a man on the moon to playing Halo on your Xbox. And we're going to replace that. Instead of silicon chips that we're working with, we're looking at doing computation with subatomic particles, like electrons, neutrons, and whatever tron you want. Don't let the idea that we're going to rip out all of the binary side of the house. You know, if you have a regular computer, you've got a quantum processor, a GPU that does processing for graphics. All we're talking about is adding in a QPU, a quantum processor, for those kinds of things that can really work with those kinds of problem solving. So really what we're looking at is replacing a bit in these instances with a qubit. And that's what we want to begin exploring. Why do we do that? What does it bring us? What's the big deal? These are things that we're going to look into. So when you ask the question, like, what makes it so special? Why do I care? Well, you got two reasons. The first thing is you have access to qubits as opposed to regular binary bits, which are a one-to-one comparison. Qubits allow you to compare parts to parts and in pieces and things like that. That changes the comparison game. You can encode more information and differently. That's different than a standard bit. The second reason why this becomes so special is because now we've got access to quantum phenomena, and that allows us to compute differently. So we're going to look at those two themes in detail a little bit, what a qubit is, what quantum phenomena are, and why that's so special. So qubits. If you look at this sphere, the best way to conceptualize this is a sphere with a projected disk on the bottom. You know, and qubits are bits, right? At the end of the day, they're either 1 and 0. But like a top, any of you guys ever spin a top when you're a kid? You know, spin this thing around, it kind of wobbles around and stops after a while. But if you spin that top, while it's spinning, you can do some really interesting calculations. So we can encode information on the qubit once we spin it up on the surface of the qubit itself as well as on the disk. So we've got what's called magnitude and phase encrypted data, where we can put data in there. And both of those, like in the binary world, you have logic, binary logic that allows you to do computation. This is how we kind of take theories and manifest themselves in physical realities. Well, you've got the same doppelgangers here too, but it's quantum logic. You've got quantum logic for phase on the qubit itself, the surface of the qubit, and phase logic on the projected disk. This allows you to do a lot of very interesting calculations. This is one of the reasons why quantum is so special. The second is that we've accessed this inventory of quantum phenomena that just does not exist in the classical world. You're dealing with subatomic particles to do calculations on, and you're rotating them around to figure out how you want to do, how those calculations actually accrue. You're looking at quantum waves, the duality between quantum waves and quantum particles. That's enough to make your head hurt. Qubits and superposition. Think of a top, right? You take a top, standing in your hand, you can't do any calculation on it because it's a dead stick. You spin that top. While it's spinning now, you can do some very, very interesting calculations. Once you do the calculation, you got to pick up the top, measure it, and then start it again. So that's a qubit. But it gives us this idea of quantum interference, which we're going to explore next. When you do calculations in the binary world, it's a pretty static kind of comparing one to another. When we do quantum interference, what we're really looking at is using the quantum phenomena of interference to influence whether that qubit gets measured at a 0 and 1 when we choose to measure that. We'll look at that in detail. Quantum entanglement is another one of those phenomena that doesn't exist in the classical world. Quantum entanglement is kind of like marriage, right? When you're a single guy, single girl, lady, you've got your own flat, your own money, your own car, your own personality, right? You get married, now you share all those things, right? And the unique things of that, you can entangle two qubits, spread them across the galaxy, hundreds of light years away. What happens to one automatically happens to another with certain caveats. And then you've got quantum teleportation, which is really how quantum networking gets done. Those of you who are Star Trek fans, that's a reasonable analogy from that to kind of wrap your head around that. But these are all the things that we have. However, well, let's get into this. let's talk about interference. Interference is kind of like you drop two pebbles into a pond, waves come around, they begin to interfere with each other. You can have additive interference or subtractive interference, what we call constructive interference. Two waves hit, you get a bigger wave. Two waves hit on the destructive side, it evens the thing out, and you don't have any waves at all. This is how we compute in the quantum space. Very different than you compute in the digital world. We're using something very, very different. It's not just bigger, faster, better. It's different, completely different. And that's one of the key things there. And it's extraordinarily powerful. But it comes at a cost. You don't get these things for free, right? So unstable wave function, you spin that top, do a bunch of calculations on it, the top could, after a while, fall off on its own. And so we call it decoherence, where the material science to hold that subatomic particle long enough to do information processing on it well just isn't mature enough to hold it robustly. They're getting there. You need reversible functions. You guys know why you have a heat sink on your CPU fan? Because when you do calculations that don't quite add up, and they have to decouple those, it creates heat. So you have to have a fan to pull that off of your CPU. That heat causes decoherence significantly. So you have to have functions you can reverse to minimize the heat. It's just one of those things at the moment. No cloning rule. Take A, put 5 into it, copy A to B, B's got 5. You can't do that with quantum phenomena. It's just one of those things. Destructive reads. Spin the top, do a whole bunch of really cool, interesting calculations on it, pop that top, and then read that qubit. You get the read, but then you go back, read that qubit again, it's dead. So you have a destructive read. These are very different than the binary world that we live in. Assembler-like programming. Raise your hands, whoever programmed assembler machine language here, machine coding here, right? How's your therapy bill treating you, right? Exactly. People hate it. It's horrible, but it's really kind of everything you do kind of bears down into machine code at some point in time or another. Programming and quantum in its current state is kind of like that, and very much like that, as a matter of fact. You'll see that. No for loops, right? No abstract programming concepts because of its level of maturity right now. And all that means is that there's a horribly restricted problem space at the moment. It's not really generic. So we can only really solve those problems that are quantum friendly or quantum force friendly. We take a problem that's not friendly, break it apart to little parts that are friendly, we solve those. So this all comes at a cost at the moment. Now, here's how you compare things. Binary computation had a theory of binary computation. Big guys with big math heads got together and created this theory of computation, and then we do what humans do. We manifest that in the physical world. That's our nature. And we tried hydraulics, and we tried mathematics, and we tried mechanics initially for binary. And then we moved to vacuum tubes, the big old AM radios, down into solid-state transistors, if you remember the beach solid-state transistor radios used to get. And then on silicon chips as we move forward. This is sort of the history lesson of how binary computation came about. Quantum's doing the same thing, but you get different names like superconducting circuits, trapped ions, yada, yada, yada. They're experimenting with physical substrate to hold that subatomic particle long enough to do good processing on it. It's not solid yet. It's not as solid as we want, but they're making tremendous progress. You just got to realize we're in that intermediate phase right now. What else? Ooh, where's my thing? Now, there's a lot of noise in this space, like there's not a lot of noise in the AI space. One of the ways to drop the noise down to really clear the room from the smoke is to look at the difference between a producer and a consumer. Producers make the tech, consumers use the tech. The moment you look at that frame, the noise drops to the floor because the producers are out making a lot of noise trying to figure out how the tech might work when they manifest it in physical reality. Almost everything you pick up is geared towards that. Pick up any quantum book. It's either opaque mathematics, material science, or dense quantum physics. Hardly anything for the consumers, and that's you guys. And that's us. Like, I'm going to use quantum computing to solve a problem. How do I do that? And that's the area that I want to focus on, and that dichotomy helps us drop the noise in the marketplace. Here's one of the reasons why. If you look at the history of computation from the abacus back way before anyone was born, all the way to present-day true mobile computing, something special happened between 1969 and 1973. Dennis Ritchie came out and invented the C programming language in Unix. That effectively moved computation out of the big data centers with these crazy guys with glasses all the way down to the hands of the people like you and I. Once that happened, like things mushroomed and money exploded and all these kinds of interesting things because the everyday person began to use their creativity in unique ways, which is really, really, really what we want to do. Now, that has to happen in the quantum computing side. We just don't know when, where, what it looks like, but we know that event's going to appear in the event horizon, and we're looking for that. So keep that in mind, too. That helps drop the noise a bit. But as a maturity analysis, let's look at this. And there's a caveat to this. So material science is not there yet. That means there's no quantum debugger, no quantum RAM, there's no quantum ID, no for loops, no abstract programming concepts, and no quantum OS. Now, there's a caveat there. I did mention we're in a global technology arms race. China just released a note the other day saying, guess what, guys? We've released a quantum operating system, and it's open source. So there's things going on around the globe that we need to take into account here. Whether that's true or not, it remains to be seen, but it's definitely something to take stock of. Now, two things. Mapping real-world problems to quantum circuits, and we're going to look at circuits in a second, is very, very difficult for the best of folks to do that. Imagine using a quantum circuit, which I'll show you in a minute, or simply assembler programming to solve very complex problems. It's painful, painful. You need to abstract that out. We don't have that yet. And because we're programming with interference, that influences the probability to be 1 or 0 somewhere in that spinning qubit when we spin it up into superposition. So these are not one-to-one comparisons like in the binary world. They're parts and pieces to parts and pieces, and sometimes lots of parts and pieces to lots and parts and pieces into a probability, which is a statistical thing. So this is what makes it hard. Now, here's a timeline. Here's this enabling event that moves us from the producer area to the consumer area. And we're all here. Producers and consumers are really early on here. This is our current state of where we are. So the producers are going to make a lot of noise. The consumers need to look for that. And even if we begin to get our organizations up to speed in quantum early, there's a lot of work to do, just basic conceptual, linguistic work that needs to be done for literacy in this space. So the consumers need to prepare their organizations now for this quantum eventuality that we don't know when or how it's going to occur or when it's going to come, but we know there's a lot of people with a lot of money across the globe working on these problems because they're important to solve. Now, quick review. Restricted problem space, assembler-like programming, educational divide, difference in times, and quantum solutions in the circuit boards uber hard. This is the current state of the world right now. But people are still working on this, and they're still making progress, and they're still doing great things. It's just very tough at the moment, like anything. So let's look at a qubit. So here's a qubit, and if you've never seen one, let's look at one. So here's a qubit. You can move it up and down. You can do all kinds of things. Here's a qubit. The 0 is here. The 1 is there. You can see that it's projected onto a disk. And if I put a Hadamard gate on that, it's a fancy term for when we make that qubit into superposition, that's what it looks like. And all we want to do is rotate this around and try to move this sphere in certain ways where we can influence it to either more 0 or more 1, and then we can encode information on the surface as well as the projection here. So if you've never seen a qubit, now you've seen a qubit. Now let's go back here. Oops. And let's look at a circuit here. So here's a quick circuit. This is a circuit board, right? These are qubits along the horizontal here. You can see one right there. We can measure it and things like that. And if I put a Hadamard gate here, that is now in superposition. Now if I want to entangle that, I just do these other couple of things here. Now we've got 2 entangled disks here. If I move this out, you can see these little ends are green because it's measuring those things. The moment I put this other thing here, I won't have to bore you with that, it gets in the middle and it quits because that qubit's entangled. And we can do all kinds of really interesting things with an entangled qubit. Let me go back here, and let's move into solving problems. Quantum speed. Let's look at this. So you guys like problems. Everybody loves problems and puzzles and things like that. This is called Of Tigers and Kittens. And we got 2 boxes. One has a man-eating tiger, and the other one has a cute kitten. They both have notes on them. One note says, either both of these are true or both of these are false. So now you've got a problem to solve. And you can use a digital solution for this, right? You've got a tiger in one, kitten in another, so you've got two boxes. And for those who remember digital logic, back in your graduate school days, you can use these gates like this, and NORs and NOTs and XNORs and all that kind of stuff to create a solution. So here's a NOT gate, here's an OR gate, here's an XOR gate, and I can create a digital solution to that. And if I run 4 iterations, 0, 0, 0, 1, 1, 0, 1, 1, 1, in both these boxes, I'm guaranteed to find where that kitten is, which we know is box 2 because we're kind of cheating. However, that's a classical way of doing digital logic. Perfectly fine. But if I have a caveat that says you can only run that circuit once, and you need to find that out, you need to look at that circuit run and have that circuit hold all of these runs at the same time simultaneously, that's when quantum comes in. So you create this quantum circuit down here. You get the 2 boxes right there, ignore these other 2, and you apply quantum logic of the same stripe. Here's the OR, here's the NOT, here's the XOR. There's a couple other crazy quantum computing things here. And as we run that once, it finds out that that kitten is in box 2. Let's go do that. So I'm going to do this. Kitten and tiger, one of my favorites. Nothing is here. I'm going to run this program once. All of a sudden, here is the resulting algorithm, and I'm going to walk you through that. And we know that that box B contains that tiger. So let's go look at that. The beauty of this is you can actually step through this. There's 2 boxes here, the ones you want to pay attention to. We're going to execute a Hadamard gate down here, and all of a sudden, all these 4 things are in superposition. We're handling all those possibilities at once. We apply the OR gate, the quantum OR gate. By the way, did you notice that? Let's go back here, right? We're going to apply an OR gate. See how those things change around? That's how quantum interference calculates. Then we're going to apply the NOT gate. It applies again. Then we're going to apply the XOR gate. Quantum interference does its thing again. Very different than classical computing. We'll do a couple of other things that I don't want to go into to bore you. And uncompute what we call a Grover mirror. And we find out that that box 2, if we go over here, you see that little 1 there. I'll see if I can make this a little bigger. That 1 there tells us that the kitten is in box 2. We did that with 1 run. That's quantum speed up, if you've never had an opportunity to see it up close and personal. Let's see what else we could do. Searching differently. Grover's algorithm for searching. Imagine you had 10 million people in a room, and you need to find one guy, because searching is a serious issue when it comes to the size of your input base. You had to find a guy who's 7 feet tall, blonde-haired, blue eyes, and male, and full of muscles. 5 things, right? The interesting thing about Grover search is when it begins to iterate, it takes all the stuff that's not what you're looking for, gives it a haircut, and plugs it on the thing you're actually looking for. So if you run it long enough, the only thing left standing is the thing that is kind of how it works. Let's go look at that. It's a weird idea to get your head around, but there's an oracle here. This is the first iteration of its run. Really nothing much there. Second time, and I'm going to move my cursor over here. You can see in there where it says 25.83. Can you see that? Yeah, your video is way better than mine. The next time we run that, now we're up to 60%. That's 2 terms in this case. The third time, we're up to 89%. The last time, we're at 99.91. So regardless of input size, you can have a small band of iterations, and you can search and find the thing that you need. These are, that's the searching mechanism. It searches differently than you could in an algorithm that must compare 1 to 1, as one whole thing to one whole other thing. You can compare pieces and parts. That makes search a lot different too. Let's go back. Oops, sorry. All right, so where can you use quantum? Everywhere. Drug discovery, enzymes, small batteries, traffic simulation, optimization, trading strategies, marketing strategies, radar, all these other kinds. Cryptography is a big thing. So quantum sensing, quantum computing, and quantum networking are the 3 big ones. Quantum computing is the most immature of those 3. So let's look at optimization. If you look at how quantum does things different than classical, and you're looking at sort of an optimization of something complex like traffic patterns. And computationally, when you look at classical computing, you've got to kind of go over these big hills here. You know, you've got classical computing, you got to go over a local maximum down to a local minimum, up and over again. It takes a lot of computational power. Quantum annealing doesn't work that way, and quantum tunneling doesn't work that way. They just go through the mountain itself. And so it's a very efficient process to get to the most optimum state very, very quickly. And so you can see that in before and after things. All these red smudges here are traffic jams in the large metropolitan area. And then when optimization techniques are applied in the quantum sense, you see that things are more spread out. There are very little of those red dots here, and then coverage has been expanded. So this is the kind of stuff that quantum does really, really well. Polygenic risk scoring and epistasis. This is one of the areas I got my patent on at Optimum UHG. You can imagine when you are comparing parts of genetic materials to figure out where things are happening. Epistasis is one of those where genes can turn on, turn off, interfere with, or do all kinds of other things. And if you look at it, just the opportunity to linearly compare all the things you need to compare is a very difficult process. But when you look at the gene expression and approach from a quantum perspective, it's much more manageable because of that, the way that quantum can hold lots and lots of possibilities in mind at the same time. Now, who's using this? Well, everybody in the government, pretty much. All of these agencies are using quantum in one form or another. There's a quantum initiative that's happening out there, and a quantum segment of the government that has been operating for a long time. So the government's well aware of this, and many of these agencies may not be putting this in the front headlines, but they're definitely working on this kind of stuff. So where does this leave you? Well, what I want to do is combine all this conceptually into this concept of looking at the human body as a computational platform. We want to compute on the body. We want to move sensors that have quantum in it and some bio stuff and some nano stuff along with AI, and move computation for monitoring folks in the healthcare space to the human body. Rings, watches, headsets, glasses, shoes, socks. There was some really great posters up there about this kind of stuff last night that I previewed, and it was extraordinarily exciting because from the healthcare perspective, we want to move towards keeping people healthy. And that means looking at the human body and doing computation on the human body. And we can do all kinds of stuff. So we're moving from mainframes to personal computers to mobile computers to on-the-body computing, and with all kinds of devices. Tremendous area for innovation and research and changing the tide of healthcare in our country. We can paint sensors at room temperature on your skin that can do some interesting things. You can swallow smart pills. We can put things subcutaneously. I mean, you know all this because it's kind of where you live. But these are the things we can do. Now, this is interesting. We're going to turn left a little bit and talk about disruptions to our biology. And you get folks like Klaus Schwab from the World Economic Forum, who I endearingly refer to as Colonel Clink, for those of you who remember Hogan's Heroes. Yes, there's a lot of Hogan's Heroes fans out there. Okay. You also know who the older people are in the room by that reference as well. But he came out and said if you master synthetic biology, and that means biotech and nanotech and some quantum in there, as well as artificial intelligence, he's looking at blurring the lines of human evolution between physical, digital, and biological kind of spheres. This is interesting. And the US government is not taking that line down, so to speak. There's an executive order on advancing biotech. This was in 2022. And these words matter when you look at that. So we need to develop genetic engineering technologies and be able to read and write circuitry for cells and predictively program biology in the same way we write software programs. Unlocking the power of artificial intelligence, blah, 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 blah. This has been going on for a while. This is kind of some of the technology that's been out there, some of the realms of research that's been happening out there. This is a big deal. We're playing with these kinds of things. Humans like to play God. And I am out of time. But the big question is, before we go to Mark here, is what could possibly go wrong? So with that, And by the way, Oppenheimer said that when you see something technically sweet, you go ahead and do it. And you worry about the ramifications afterwards. Oppenheimer, father of the atomic bomb. Anyway, thank you all for your time here and allowing me to present to you.
Yeah, that's fine. All right, it's time for Q&A, and go ahead. Who is the first one to take the shot? Go ahead. I thought there was enough sugar in the desserts. Maybe put them to sleep, you think? Hello, any question? Anybody? Yes, please. Thank you.
Okay.
Yeah, let the ball rolling.
Sure, it was a great talk. Yeah, I studied computer science. I was wondering about your talk. I actually curious about the sorting problem. And traditionally, sorting is like we formalize like the time that it takes is like O of n log n, and how it works in computing, quantum computing system. Yeah.
So in classical computing, you have the big O notation, which every computer scientist absolutely hates. That's just one of the things they despise right after machine learning, machine coding, machine level and assembler coding. Those are based on binary computations with some heuristics that get involved to help make that smarter. And those algorithms might use small little changes to get better. But the computation, the data size that it has to sort through always plays into that. When you use the quantum side of the house, that doesn't exist anymore. You're not sorting, you're not searching in that same way. You're doing it differently. And that's why we can search through 10 million with 5 iterations. So it's a different method of searching. And it's a different method of computation. And that's what makes it different.
So you have some matching, some annotations like O of something, or like is O of like a constant now?
Those don't even apply. It's not even part of that conversation. Yeah, that's what makes it weird, because you got to wrap your head around this, and some of us are like, I don't think I can.
Very interesting, yeah, amazing.
All right, next.
Next question, the gentleman there.
Thank you. I guess could you talk a little bit more about why we don't have the circuits? Is it some technical factor, like it needs to be cold temperature, supercooling, magnetic fields? What is it that's holding us back? Second question is that relates to that is, if you don't mind my giving you 3, I'll give them, they're entangled, so partly to make it easier for you.
It's all good.
So the other is, what then becomes the energy consumption of whatever the hardware is? Because we're obviously very concerned about that with regular computing. Mm-hmm. And finally, is it only speed that it does better, which is why people are talking about it for encryption? I mean, if you could just speed up the binary operations, what is it that the quantum process actually gives you that's somehow qualitatively different?
Yeah, okay. I may have to tap you for each one of those parts again. Let's do the last part.
Do it, you're stuck.
All right, I'm good. So the last part, like, what makes quantum so different than classical computing? Like, what's the big deal? Like, what does it actually give us? Well, the qubit, for one, that's different. You can encode different information in that, and it's got its own logical contracts to do logical reasoning over that. But then the second is you've got all this quantum phenomena just don't exist. It just doesn't exist in the classical world. So you can compute the process of computing through influencing, through that influencing, the interference that influences that qubit to move towards 0 or 1, combined with the different ways and modalities of encapsulating information in that qubit and the logic associated with that, allows us not just speed, but search and the ability to tackle problems that are unapproachable from a classical computing sense, that are just too big or too odd or too weird. Plus, what's the word I want to use? The quantumness of itself tends to model the real world a little bit better than classical non-quantum physics, and so we can attack some problems that are fairly unique. So there's this whole host of problems. You can't think of it as quantum replacing classical computing. It's an augmentation to it. I think that's a better way to look at it.
The other questions had to do with the hardware limitations, and if we get the hardware, is it going to, warm the planet faster than we're doing it already.
So I can't, so the real reason why you're not seeing things cascade, like they're massing at the border, all these entities are massing at the border, like waiting for that foundational aspect to get fixed, and that is how long can I hold a subatomic particle with and how well can I hold that to do, and reliably to do information processing on it. They don't yet have that set, but once they do, there's all kinds of stuff on the drawing boards that will move forward extraordinarily fast because they all hit that same wall. So once that material science and basic physics kind of crack that nut, then you'll see a flood of innovations coming in that space. As far as the energy consumption, and I don't think it's appropriate to compare that to the energy consumption for large foundation models where you're thinking of dropping in, portable nuclear power plants to begin to begin to help power these big data centers. I don't think it's that same way. It's much smaller, and it's too immature to really kind of peg that just yet. So, but I don't think it's going to be the same.
Thank you.
Others?
Next question? Yeah, please.
So my program here at A2 was designed for low-income older adults, but we had a really hard time recruiting that population for our study, which was nowhere near as difficult to explain as yours will be. So we all know that the best technology makes no difference if people won't adopt it.
Okay.
And how are you thinking about moving your technology from the worried well to the people who actually need it in order to improve their health care?
Good point. You have a cell phone with you, right?
No.
Does anybody have a cell phone with them? Okay. Do you know what's in that cell phone, how it works mechanically and electronically and all that? Not really. You just care what it does. And AI and quantum is going to kind of be the same thing. If we can manifest the user interface and the capabilities to where they can help everyone, that's really the goal. What happens abstractly and scientifically under the hood, nobody really cares about.
But the point is that they won't let you near them to do that. And
They won't let you near them. Help me out with that one.
so our ability to recruit for our study was just observational. It wasn't even touching them.
Okay.
And I know from my user interviews that anything that touches a person is much more difficult to get into a person's space than something that's just observational. And we can look at a camera and say even taking a picture of somebody can be, privacy invasive for some people.
Okay.
So when you're talking about putting on socks and rings and shirts and bandanas and everything else that is collecting all that data that you're collecting, I mean, I would love to have the answer that will help the people who need it most, but I also believe that they'll be the most resistant to doing the things that you would like to do.
Yeah, I think that's been the case for history. As long as history's been around, these technological innovations, you'll get people who either can't get to them, who should, or who can get to them but are leery of them because there's the fear factor. And with AI, as well as quantum, not necessarily quantum, but AI tends to have this ew factor where it's like, ew, this thing's a little more real than I thought it was. All of those things play into that. I don't know if that's a technological concern, though. I think that's a people concern. And I think that's where the answer lies.
Yeah, I think we can all agree that it's a people concern. But again, if you have the best technology in the world and the obvious user isn't willing to use it, how do we overcome that? And that was my question, is essentially, how do you think about that problem of overcoming the fear factor? The respect, the dignity, and all the things that we've heard from other speakers about convincing somebody or providing an opportunity to make somebody better with a value proposition.
Yeah, the last person I would ask is a technologist to solve that question. So, other questions?
Are there other questions? Yeah, please.
Yeah, Mike, I think you said there are certain questions that are not appropriate quantum questions. I said that early on? Maybe
no,
not?
I would say let it rip. You can play stump the presenter if you like. It's all right.
Okay, so my question is, what is a good quantum question and what is not a good quantum question. So I was asking because you had the body as a computational model,
Yes.
right?
Yes.
It's physics and biology and genetics and lots of different fields that you have to understand the mechanisms and many things that we don't understand to see the body as a computational model. So is it the complexity? Is it the features? Is it like what makes something a good quantum question?
I'm trying to relate that to the body as a computational platform, and I'm struggling.
Yeah,
to
because
do
you said
that.
that was like a quantum thing.
Well, it's an AI thing. It's a people thing. It's a healthcare thing. It's a thing that we see if enough innovation happens that can monitor. And I'm kind of moving a little bit away from the quantum side, but as we look at healthcare moving more towards prevention, it's kind of like fraud, right? The winning is in preventing fraud, not in clawing back money that's been stolen from you. Same thing with healthcare. If we can keep people healthy, that's the win, rather than fix them once they've gotten very, very ill. And so the ability to monitor the human body with very sophisticated sensing capabilities that are tied to very powerful AI on the edge that can do interventions with those individuals in advance of clinical emergencies can, at large, across the entire population of how many million people we have here, can literally shift healthcare into that wellness health space, which is where we really want people. And that's where I think things are going.
So that was kind of my question, because that question, to solve that, you need to know biology and physics and behavior and, all the, a whole bunch of fields. And you have to
AI,
actually ask the
yep.
same question from
Yep.
multiple perspectives at the same time.
Exactly.
Is that a good quantum problem? Was kind of my question.
It's a quantum thought process, but I don't think the technology runs deep in that on that side of the house. But that's where I see healthcare going.
Thank you for a very interesting introduction. I really enjoyed it. So I have two questions. One is, if we look at the companies doing quantum computing, stock of those companies growing like 100-folds, right? So question number one, very practical, which one I should buy?
And the second?
I'll tell you after you answer my first one.
Yeah, I can't weigh in on that one, sorry.
Okay, cool. Maybe we could grab coffee afterwards. My second one is the bottleneck of AI models is typically fitting parameters and estimation of deep architectures. Do you see any work re-envisioning architectures which will be more suitable for quantum computing, which would work much?
So quantum computing architectures in general probably won't interface that much that we can see at the moment, except in the machine learning space where you've got error weights that can be more accurately, more nuanced, computed that way. But you've got three things to concern about when it comes to AI. You've got three epochs of evolution there you must differentiate with. You've got the classical AI, machine learning, data science, machine learning, deep learning, all that stuff you've been steeped in to date. It's mature, it's growing. The moment you move into generative AI, when you go into large foundational models, large language models that kind of fit in on that as just sort of an interface, you change tech stacks. You move from a statistical thing to a vector kind of database that does semantic matching but doesn't really get the whole foundational ground truthness to it. The moment you move right one more instance, you get into agentic technology. Agents, intelligent agents that can think and reason and behave on their own without human intervention. The best way to figure that out is go grab your kid's Xbox or PS4 and play Halo or Call of Duty. And you get those monster factors that put the bad guys out there. Those are intelligent agents. And that's another different tech stack. So each one of those has to be treated differently on n number of dimensions.
Rose says I should stop, but my colleague, Professor Jerry Prince, who has a question, if I don't let him ask, he won't talk.
I'll be mad at you
Yeah.
forever, Rama.
Yes, I know. That's why. Go ahead, Jerry, quick one.
So we've been told for many years that when quantum computing becomes real, it will end the security of our bank accounts. That's question number one. Question number two is I can't reliably tell AI videos on YouTube. Will quantum computing be able to tell me the difference between real and artificial?
So the first one, when you hit 1,000, theoretically, when you hit 1,000 qubits, like good solid qubits that you can work with, you can break the weak encryption on blockchain. But that's weak encryption. It's not necessarily strong encryption. But that doesn't mean that as further advancements in the quantum space go, like what we're seeing coming out of China and some other folks, that capability might not be around the corner. So the ability to take encrypted important data from governmental and other important institutions and put them on the dark web with the hope that you can decrypt them in 10 years because the technology matures, that's a real thing. As far as the deep fakes go, good luck with that. I don't know that I've got an answer for that, but that's a thing. You know, when you can't reliably trust what you see, hear, or read, how do you authenticate, like, authenticity? And that's a big problem.
So with that, let's thank the speaker for a delightful talk. And the next session, please.